Okay, so welcome to the deep dive, everybody. Today we are going to be tackling
Sounds fun.
a really interesting topic
Mhm.
that I think a lot of people are probably familiar with to
That's
some
correct.
degree, but hopefully we'll be able to cover it in a new and exciting way today.
All right.
So that is the topic of dark matter and dark energy.
Okay.
And for people who aren't already aware, this stuff basically makes up 95% of the universe,
Wow.
which is kind of a crazy thing to think
Yeah,
about.
that's a lot we don't know then.
It is. So
Yeah.
everything that we can see, the stars, the planets, the galaxies,
Yeah.
all the stuff that we're made of
Right.
makes up a measly 5%
Really, just 5%?
of the known universe.
Wow.
So, yeah, kind of crazy.
That's more than a little humbling, isn't it?
It is. It is.
To think everything we've ever observed is just a tiny fraction.
Yeah, and it really puts into perspective just how much we still don't know
Exactly.
and how much there still is out there to learn. So I guess you could say that we're kind of like explorers going on this journey together
Okay, I like that.
to make sense of these really mind-bending ideas.
Yeah, let's dive in.
We'll do our best to kind of explain them in a way that hopefully is approachable
Yeah.
and easy to understand. But yeah, it's going to be a wild ride.
I think it's incredible that 95% isn't just empty space.
Right.
It's not like we're missing a few puzzle pieces here. It's this huge unknown presence that's actually shaping the universe.
Yeah.
Yeah.
That has a real effect
Yeah,
on the things that we can see.
absolutely. And that's what makes it so fascinating to study.
Exactly. So when we talk about dark matter, we're talking about this really elusive thing. You could almost think of it as like the universe's shy, introverted cousin.
Okay.
It barely interacts with anything.
It's like the cosmic wallflower.
Exactly. It doesn't even interact with light.
That's why it's so hard to even detect.
Yeah, that's why we can't see it. So
Yeah.
let's unpack how we even got to the point of knowing that this stuff exists.
Yeah. How did we figure out something was there if we can't see it?
Right. So the first clues for dark matter actually came from astronomers looking at how galaxies spin.
Galaxy spin.
Yeah, so
Okay.
think about our solar system. Right, so you have the sun at the center,
Right.
and then the planets orbit around it, and the planets further away from the sun orbit much slower.
That makes sense. The sun's gravity is weaker further out.
Exactly, and that's because
Okay.
the force of gravity decreases with distance.
Right. So it's a nice predictable system.
Right, it's like a cosmic ballet.
Exactly. And so scientists initially thought that the same would apply to stars within galaxies.
Okay,
Stars closer to the center would be zipping around much faster than those further out.
that makes sense, yeah,
Okay.
because the center of the galaxy
Yeah.
would have the strongest gravitational pull.
Right. All that mass concentrated in the middle.
Right.
Yeah.
Then they started looking at these distant spiral galaxies,
Okay.
and they found something really weird.
What was that?
The stars at the edges of the galaxies
Mhm.
were moving way faster
Really?
than they should have been,
Well-
based on the amount of visible matter that was there.
So like the visible stars and gas weren't enough to explain those speeds.
Exactly. It was almost as if there was way more mass holding those galaxies together.
Interesting. So like there was some invisible source of gravity.
Right, than what we could actually see.
That's wild.
And so this mismatch between the observed speeds of the stars and the amount of visible matter was a really strong indication that there had to be some kind of invisible matter that was providing this extra gravitational pull.
Dark matter.
Yeah, dark matter. It's like, imagine a figure skater spinning really fast.
Okay.
Like so fast that their arms should just fly off.
Yeah.
But something invisible is keeping them glued on.
I like that analogy. It really captures the idea.
So that invisible force is like the dark matter.
And it's not just preventing galaxies from flying apart.
Right.
It also played a key role in how galaxies formed in the first place.
Okay, so we know it's there because of its effects.
Yep.
But the big question is,
What is it?
what is this stuff? So scientists have come up with all sorts of different theories about what dark matter could be. And one of the most popular ones for a long time has been the idea of
Weakly interacting massive particles.
weakly interacting massive particles.
Which is a mouthful.
It is, but luckily we have the acronym
SOAPMEs.
WIMPs. And the name kind of gives you some hints about what scientists thought these things might be.
Right, break it down for me.
So massive implies that they have a lot of mass.
Okay, that makes sense. Massive things have a lot of mass.
Right. And in fact,
Yeah.
the source material actually mentions that they could have masses of several TeV.
Several TeV, that's pretty heavy.
Yeah, so for anyone who's not a particle physicist,
Mhm.
which is probably most of us, can you put that into perspective?
Sure, so a TeV is a tera-electron volt,
Okay.
which is a unit of energy, but in particle physics, we often use it to describe mass because of that famous equation, EMCO.
Right. Energy and mass are basically two sides of the same coin.
Exactly. So to put that into perspective, a proton, which is one of the particles that makes up an atom's nucleus, has a mass of about 1 GeV or giga electron volt.
Okay.
So a TeV is 1,000 times larger than that.
So we're talking about particles that are potentially thousands of times more massive than a proton.
That's right. These are heavy hitters in the particle world.
Wow.
And because they are so massive, it's thought that they wouldn't be zipping around at the speed of light.
Okay.
Instead, they'd be moving much slower, what we call cold dark matter.
Cold dark matter.
Yeah, so their average speed would be well below the speed of light.
And why is that important, the speed? I mean,
Well, it turns out that the speed of dark matter particles would have had a major impact on how galaxies formed.
oh, really?
Yeah, if they were moving too fast, they wouldn't clump together gravitationally,
Okay.
and they wouldn't be able to provide the scaffolding for galaxies to form.
Oh, I see. So
They need to be slow enough to kind of hang out in one place and exert their gravitational influence.
like the cosmic glue that holds everything together.
Exactly.
Okay, so we've got massive. Let's talk about the weakly interacting part.
Right, because that's the other half of the name.
Right. So this means that they're predicted
Yeah.
to only interact with other matter through the weak nuclear force.
The weak nuclear force.
Yeah.
Okay, so that's one of the 4 fundamental forces of nature.
Right.
But as the name suggests, it's very weak.
And it only acts over extremely short distances.
Yeah, it's kind of like the shy introvert of the force world.
So because of this, the chances of a WIMP actually interacting with a regular particle are incredibly low.
Yeah, like astronomically low.
Which makes them extremely difficult to detect.
It's like trying to find a needle in a cosmic haystack.
Yeah, and the source mentions that WIMPs are predicted to exist in theories like supersymmetry and extra dimensions.
Right, so those are some pretty mind-bending concepts.
Yeah, so for those of us who aren't theoretical physicists, can you kind of give us a simplified explanation of what those are?
Sure, so supersymmetry is essentially a theory that proposes that for every known particle in the universe, there's a corresponding partner particle.
Okay, like a mirror image.
Exactly. And some of these hypothetical partner particles could have the properties of WIMPs.
So it's like a whole new set of particles
That's it.
that we haven't discovered yet.
Right, and extra dimensions is the idea that
Yeah,
our universe might have more than the 3 spatial dimensions that we're familiar with.
right. Length, width, and height.
Exactly. So imagine like a 4th spatial dimension we can't perceive directly.
Whoa, okay.
And these extra dimensions could contain particles that behave like dark matter?
Okay, so it's like there's this whole hidden realm that we can't see
Kind of like a shadow universe.
where dark matter might be hanging out.
Yeah, it's a fascinating idea.
It is. So there have been a lot of experiments
Hmm.
to try and detect WIMPs. One of those famous ones
Yeah.
was the Large Underground Xenon Detector, or LUX.
LUX. Yeah, I've heard of that one.
And this thing was built deep underground
Why underground?
to shield it from all the other radiation.
Oh, that makes sense. You don't want interference from other particles.
Right. You want to make sure that if you detect something, it's actually a WIMP
Yeah.
and not just some other random particle.
Smart.
So they ran this experiment for several years, but unfortunately,
Mhm.
they didn't find any conclusive evidence of WIMPs.
Oh, that's a shame.
It is. But the search continues, with even more sensitive experiments being planned.
That's the spirit of science. Never give up.
Exactly. So WIMPs are still a possibility,
Mm.
but the jury's still out.
Fair enough.
So let's move on to another popular dark matter candidate,
Okay.
and that is Axions.
Axions, all right.
And these are very different from WIMPs.
How so?
Well, for starters, they're predicted to be incredibly light.
Okay, so instead of massive, we have super light.
Right. The source mentions that they could have masses on the order of microelectron volts.
Microelectron volts. Wow, that's tiny.
Yeah, so compared to WIMPs, they're like feathers.
So what about their interactions? Are they also weakly interacting?
Even more so, axions are not predicted to interact through the electromagnetic force.
Yeah.
Or the strong nuclear force.
So they're practically invisible to us then,
Yeah.
and not affected by the force that holds atomic nuclei together.
Right. So they're incredibly difficult to detect.
So if they're so light and barely interact with anything, how could they possibly be dark matter?
Well, that's a good question. And it turns out that they're very weak interactions.
Yeah.
And incredibly light mass. actually make them very stable.
Stable?
Yeah, they could essentially exist
Yeah.
for the entire age of the universe.
Okay, so they're like the cosmic Methuselahs of particles.
Exactly. And that fits in really nicely with the fact that we know dark matter has been around for billions of years.
That makes sense.
And despite the challenges, there are actually experiments trying to detect axions.
Oh, wow, really?
Yeah, like the ADMX experiment.
ADMX, what does that stand for?
It stands for the Axion Dark Matter Experiment.
Catchy?
And there's also the Casper experiment.
Casper. Okay, I don't even want to know what that stands for.
Yeah, it's a bit of a mouthful. But basically, these experiments are trying to observe the really subtle effects that axions might have on things like electromagnetism and the spins of atomic nuclei.
So it's like they're looking for the faintest whisper against the roar of the universe.
Exactly. It's a really difficult thing to do.
I bet.
Okay, so we've talked about massive and weakly interacting particles.
WIMPs.
And we've talked about super light
Yeah.
and even more weakly interacting particles.
Axions.
So what's next?
Well, there's another interesting candidate. Sterile neutrinos.
Sterile neutrinos. Okay, so
Yeah.
we already know that neutrinos exist.
Right, those tiny little ghosts of the particle world.
Yeah, they're these incredibly tiny particles
Yeah.
that interact through the weak nuclear force. And they're incredibly difficult to detect.
But we have managed to detect them, right?
We have, with these massive underground detectors.
Yeah, those huge golden chamber detectors that look like something out of a sci-fi movie.
Right. So how are sterile neutrinos different?
Well, the key difference is that they're theorized to interact solely through gravity.
Just gravity.
Yeah, no weak force, no electromagnetic force, nothing else.
Wow, so they're even more isolated than
Well,
WIMPs.
True cosmic loners.
Yeah, it's like they're practically ghosts. So how could we ever hope to find something that only interacts through gravity?
Ah, that's a great question. And the truth is, it would be incredibly difficult. But the source does mention a couple of possible detection methods.
Okay.
One is by looking for X-ray emissions from galaxy clusters,
Okay.
which might be produced if sterile neutrinos decay.
Interesting.
And another possibility is to search for subtle imprints they might have left on the cosmic microwave background radiation.
The CMB.
Exactly that afterglow of the Big Bang.
So it's like we're trying to look for the faintest shadows that they might have cast on the universe.
Pretty much.
But as with all these candidates, we haven't actually found any direct evidence of their existence.
So for now, they remain hypothetical.
Okay, so moving on, we have another interesting idea, and that is dark photons.
Dark photons,
So are these like regular photons?
but dark.
That's a good way to think about it.
Ah,
But instead of carrying the electromagnetic force, they would carry a new fundamental force,
okay.
a dark force, if you will,
A dark force.
that would only interact between dark matter particles.
Okay. It's like
Yeah.
dark matter has its own separate communication network
You got it.
that we're not privy to.
Exactly.
Interesting.
So if dark matter is made up of particles that can talk to each other through this dark force, it could potentially explain some of the things we observe about its distribution in the universe.
Yeah. Like what?
Well, for example, the distribution of dark matter in dwarf galaxies doesn't quite match what our simulations predict.
Okay.
If dark matter particles were only interacting through gravity, we'd expect to see a much denser concentration of dark matter in the centers of these galaxies. But that's not what we observe.
So the dark force could smooth things out a bit.
Exactly. If these particles can interact with each other through this dark force, it could lead to a more even distribution of dark matter.
And the source mentions that. These dark photons might even be able to mix with regular photons.
Mix.
Yeah, it's a theoretical possibility. And if it happens, it could lead to some really subtle signals that we might be able to detect.
Okay, so that would be a way of indirectly detecting them.
Exactly. But so far, no such luck.
Okay, so no evidence yet.
Not yet, but the search continues.
So we've gone through this whole list of potential dark matter particles. But what if dark matter isn't a particle at all?
Now you're talking.
Yeah, and that brings us to the idea of emergent gravity.
Emergent gravity, that sounds pretty radical.
It is. It's a completely different way of thinking about dark matter.
All right. I'm intrigued. Lay it on me.
So instead of saying that there's this new type of particle that we haven't discovered yet, emergent gravity proposes that gravity itself isn't what we think it is.
Whoa, hold on. You're saying gravity isn't fundamental.
Well, not in the way we currently understand it. Emergent gravity suggests that gravity might actually emerge from a more fundamental phenomenon.
And what phenomenon would that be?
Quantum entanglement.
Quantum entanglement, you mean that spoopy action at a distance?
The one and only. So as you know, quantum entanglement is this really strange connection where two particles become linked, no matter how far apart they are.
Right, it's like they're communicating instantaneously,
Yeah.
even across vast distances.
And so the idea with emergent gravity is that the effects that we attribute to dark matter, like the faster than expected rotation of galaxies,
Yeah.
might actually be caused by this intricate web of quantum entanglement that permeates the universe.
So it's like gravity is an emergent property of this underlying quantum entanglement.
Exactly. It's a really mind-blowing concept.
It is. It really challenges our understanding of what gravity is.
Yeah, and it's important to point out that this is still a very theoretical idea. There's no direct experimental evidence to support it yet.
But it's a fascinating possibility.
It is. Okay, so we've covered a lot of ground
We have.
on dark matter. Now let's shift gears
Okay.
and talk about the other big mysterious component of the universe.
Dark energy. Dark energy, the cosmic accelerator.
Yeah. So this is the force that's thought to be responsible for the accelerating expansion of the universe.
Right. So for billions of years, the universe has been expanding.
Since the Big Bang.
Exactly.
Right.
And if gravity was the only force at play, we'd expect that expansion to slow down.
Right.
Because gravity pulls things together. But in the late 1990s, astronomers made a shocking discovery.
What was that?
The expansion of the universe wasn't slowing down, it was speeding up.
Speeding up.
Yeah, like someone had stepped on the cosmic gas pedal.
Okay, so what could possibly be causing that?
Well, that's the million-dollar question. And the leading explanation is dark energy.
Dark energy.
This mysterious force that's pushing everything apart.
And it's not just pushing things apart, it's pushing them apart at an accelerating rate.
Right, so the expansion is getting faster and faster.
Okay, so what are some of the leading theories about what dark energy could be?
All right, well, one of the simplest explanations is the cosmological constant.
The cosmological constant.
And this idea actually goes all the way back to Einstein.
Oh, wow.
Yeah, he originally introduced it as a way to keep the universe static.
Static. Because back then, people thought the universe was eternal and unchanging.
Right, the steady state model. But later, when it was discovered that the universe was actually expanding, he abandoned the cosmological constant, calling it his biggest blunder.
Oh, the irony.
Right, but now the cosmological constant is back.
And it's being used to explain the accelerating expansion.
Exactly. So what is it exactly?
Well, it's basically the idea that empty space itself has energy.
Empty space having energy, that's pretty mind-blowing.
Yeah, and this energy is thought to have a negative pressure.
Negative pressure, what does that mean?
Well, it means that instead of pulling things together, like gravity does, it pushes them apart.
Oh, I see.
And so this energy of empty space is what's thought to be driving the accelerating expansion.
Okay, but where does this energy come from?
Well, that's where things get a little tricky. One way to think about it is in terms of quantum fluctuations.
Quantum fluctuations.
So in the quantum world, empty space,
It's
that's actually empty. It's full of these virtual particles that are constantly popping into and out of existence.
So like a constant sea of particles being created and destroyed.
Exactly. And these particles have energy.
Okay, so that's the source of the energy.
Yeah, and so the energy associated with these quantum fluctuations is what's thought to contribute to the cosmological constant.
That makes sense.
But there's a problem.
A problem? What is it?
A big one.
Uh-oh.
When physicists try to calculate the value of the cosmological constant. Based on quantum field theory, they get an answer. That's way too big.
Way too big. How big are we talking?
We're talking 120 orders of magnitude.
120 orders of magnitude. That's a 1 with 120 zeros after it.
Yeah. So it's like trying to measure the distance to the moon and being off by the size of the entire solar system.
Wow, that's not just a little off, that's astronomically off.
It is. And so this is a huge problem for the cosmological constant idea.
Yeah, it's a major discrepancy.
Because it suggests that there's something fundamental that we're missing.
About how quantum mechanics and gravity work together.
Exactly. So while the cosmological constant is the simplest explanation for dark energy, it also comes with this huge baggage.
Yeah, a lot of unanswered questions.